Hello and welcome to this podcast for Electropages. Today here in the Philippines, because I'm currently traveling, we are joined by a very interesting guest from Bosch. Now we all know what SiC technologies are and why they're so important, but let's hear from them themselves. So without further ado, please tell the audience who you are, what you do and what you like to do in your free time.
Thank you, Robin. So my name is Ralf Bornefeld. I'm a Senior Vice President and Business Unit Head for Power Semiconductors and Power Modules at Robert Bosch in Reutlingen, south of Stuttgart. I'm a semiconductor veteran, I can call myself, because I spent, before I joined Bosch 6 years ago, I spent 15 years at Infineon Technologies in various roles, and another 14 years before at Elmos Semiconductor in Dortmund in Germany. I have a degree in electric engineering, and I'm in semiconductors all my business life.
And I have to admit that semiconductors is one of my biggest favorite areas of electronics. And funnily enough, when I was actually at university, it was my favorite module as well. I mean, there's something brilliant about designing a circuit on the transistor level where you can actually design the gates, the width, the channels and stuff like that. It's absolutely fantastic. And it's really great to have you on the show. Very, very quickly though, one more question because you didn't answer. What do you like to do in your free time?
I'm spending time with my family and my wife, and I'm like nature. So I like mountain biking, hiking, swimming. Wow. This is what I like to do. And I play the guitar. So music is also
fantastic.
Another element in my life.
Let's start with my first question. Could you just tell us a bit about SiC technologies as they currently are? Because we've seen them around for a couple of years now, and the technology is getting more mature. But could you just tell us where we currently are with it?
So I must say the silicon carbide came to the automotive world. It has been used in industrial already before when Tesla started the Model 3. This was the first car on the road using silicon carbide for the traction inverter. And this happened in the years 2017, 2018. So it's quite a while since then. And afterwards, it broadened step by step. And today it can be called as a mainstream technology in e-mobility already. So I must say, in the beginning, there were a lot of concerns about the reliability and robustness of this technology compared to silicon that got used before, and that is still used up to now. But the industry has made significant progress to bring the silicon carbide to a maturity level. And if you would ask me today where we stand, I would say we got farther than we expected years ago.
Further?
Yeah. So it
explain, yeah.
It has already reached a maturity level where, for instance, the yields are higher than we expected years before. We have managed to move faster to the bigger wafer diameter of 200 millimeters that give us the benefits in terms of cost and production economics. So these are two examples where we got faster to a point than we thought 3, 4, 5 years back.
It's funny you mentioned about the die size, because I actually remember not that long ago people were celebrating with like 100 millimeter dies, and they thought, oh, this is a great sort of advance. But then I think it's important to realize that because it's a circle, if you go from 100 to 200, I think that's a factor of 4 increase in surface area. Is that correct? Pi r squared.
Right.
So I think that's about 4 times extra space, isn't it?
Yeah. That is one benefit you have. But there's another that is very often forgotten. The tool set that you have in 200 millimeter manufacturing is much more modern than the one that you use in 150 millimeters. And these newer, more modern tool generations can improve the manufacturing significantly in terms of tolerances that you have to manage, for instance. And then the final product will become a much tighter spec'd product than what you can do on a 150 millimeter wafer. So
that's interesting to say, because does that imply that if you have your sort of production line designed for 150 millimeters, sorry, no, let me start again. Are you implying that if you have a production line designed for 200 millimeter wafers, but you try to manufacture 150 millimeter wafers, you can't actually use it on the machines because of a certain size and the fixtures and stuff. Is that what you're saying?
Yeah, and you must know. So we all started with 150 millimeter wafer size on silicon, a long time ago, and the tools that were available at that point in time and that got bought and that are still installed, they are an older tool generation than the ones that then 10 years later got bought when we started the 200 millimeter wafer fabs. And this is what I'm saying, because you have a more modern tool set, you can manufacture with much tighter specifications.
But again, that's implying that you can't actually put 150 millimeter wafers into a 200 millimeter production process.
Yes. Yeah. That's what
that's really interesting, because you would imagine that if you can make 200 millimeter wafers, you think, well, I can put 150 because it would fit. But what you're saying is, no, the machinery specifically for 200 millimeter wafers, you can't put a smaller one in there.
That's for some of the equipments. There are also equipments where you can share 200 and 150 millimeter, but not for all of the tools.
But no, and what matters is the entire manufacturing process, because you can't sort of like have bits of machinery here, bits of machinery there for different processes. You need the whole production line designed for one sort of technology. And so that's why when you say going from 150 to 200 is so important, because suddenly all the equipment that's currently there for 200 is a lot better in terms of, I'm guessing, minimum feature size, defects and all that kind, and sort of like precision in terms of stepping.
Right, and especially also the homogeneity of all the layers that you deposit, that you add. This is much more homogeneous on the 200 millimeter tool set. And this is where silicon carbide chips will benefit from. Yeah?
And a quick question on silicon carbide technology itself: is it grown as a layer on top of standard silicon, or is it the whole like bulk material, the whole crystal silicon carbide itself?
So the bulk material is silicon carbide. It's a different raw material. And then on the silicon carbide raw wafer, you grow an epitaxial layer. And this is the layer where the device later is built on. And you can only grow the silicon carbide layer on this native substrate without any difficulties in terms of material matching, property matching. And then in this epitaxial layer, you build your device.
And I'm guessing this sort of type of specialist growth of these materials is why it's also been difficult to get silicon carbide into standard process chains, because you can't just say, oh, well, if I've got a silicon production line, just do silicon carbide. Well, you can't, because you need different machines to handle that material.
Yeah, this is valid for some of the machines, because in this silicon carbide raw material, you have different conditions for instance, for high temperature process. You need to go to much higher temperatures than you do on silicon, even to 1600, 1700 Celsius, so very, very high temperatures. You need special equipment to put dopants into the material, because you need much more energy for doing that.
And I'm guessing that's because of the crystal structure being so strong compared to standard silicon.
Right, but you can also use a lot of equipment, manufacturing equipment, from the silicon space, like lithography equipment, to put one, because there you just need to train the equipment to be also capable to handle the silicon carbide raw wafer.
Now, with Bosch as a company who's in the silicon carbide space, what would you say has been the biggest challenge you have faced when trying to sort of manufacture and deploy these technologies?
So the biggest challenge was really to get the yield up to a reasonable level. And this has to do with the raw material defects and managing these defects throughout the processing of the epitaxial layer and the device layer later. And the key was really to cooperate very closely with the raw material suppliers to get their defect density down to a level where the yield on the device level came to acceptable levels.
And if you get the yields up, then the prices of these devices go down, which makes them more economically viable for products and engineers.
Yeah, and then you can put them into competition to silicon-based IGBTs, which have been manufactured for 50 years, and where you have reached a maturity level that is far beyond what we had when we started the silicon carbide.
And so would you say that Bosch has found challenges when it comes to its customers and trying to deploy these technologies? Because you said earlier about, in the early days of silicon carbide, there were issues with reliability. There were issues with people not quite understanding the technology. But would you say that that's been a challenge for Bosch?
So I must say the Bosch is really delivering. We have a brand name that is known in all of our markets that we supply. And everybody knows if Bosch delivers a product, it is a high quality product. So what we did is in the early phase, we screened out all the bad parts. So what reached our customers, this was high quality grade right from the beginning, but with a certain yield loss on our side. And this was then really the hard job that we did together with our raw material suppliers to bring that to a level. And the level today has reached a point that is even better than we thought years ago.
That's interesting. You mentioned about sort of like filtering the bad products from the good ones. Are you suggesting that when you had, let's say, a range of silicon carbide devices that you've manufactured for testing and deployment purposes, you would have devices that would be within what engineers would consider an acceptable range, but because you wanted to be absolutely sure of the highest quality, you kind of made the requirements for what you considered a good product very, very narrow and very, very strict?
This is a step-by-step process. For sure, the screening on our side was also complemented by screening at our customer side at their product level. For instance, an inverter or an onboard charger, they also had in the beginning much more screening buffer than they have today, where they know that the technology has reached a maturity grade where they could reduce their screening efforts.
Now, sort of moving back to the wafer sort of situation, because I kind of want to ask a quick question about this. So you mentioned about 200 millimeter wafers, which means that you can make more devices per area, which means you can get higher yields, better quality control, better technology, which is good for you and your customers. But forgive me, because I'm not quite sure about this, but how many other businesses out there actually are using 200 millimeter wafers, or is this something that Bosch has managed to sort of break before anyone else?
So all of our global competitors are on the way to switch to 200 millimeter production for silicon carbide. We were one of the early birds, I must say, maybe the earliest, even though, because we thought this is an instrumental move that we must make to scale the silicon carbide technology. It has also to do with how much parts you can manufacture on an existing line. If the wafer size is 150 millimeter, you need more or less double the installed production equipment capacity. And this was not a way that we took. We started 200 millimeter very early, and we were one of the first introducing this to the market.
And with this sort of transfer from 150 to 200 millimeter wafers, how would you say that's affected your ability to sort of get higher yields and reduce the price of the final product? Because I think one thing that most engineers are really looking for and what they're really sort of got their fingers crossed for is that the price of SiC devices can come down so they become even more competitive compared to IGBTs and other power silicon devices.
Yeah, so definitely. So the 200 millimeter, due to this better tool set, more modern tool set that I already explained earlier, is eventually ending up at a higher yield than you can ever achieve on 150. And combined with this nearly factor 2 of devices you manufacture on a wafer, the costs come down to a level, and they already came down to a level where it is no doubt that silicon carbide will become the mainstream technology for traction inverters, for instance.
And that's obviously down to the fact that silicon carbide devices, they operate at a higher frequency, higher powers for a given area, which means that magnetics can become smaller. And as a result, you get lower sort of weight, lower energy wastage, and which is going to be quite critical in an EV.
Yeah, it depends on the application in the EV. We have several applications. We have mainly the onboard charger and the DC-DC converters. These are operating, as you said, at higher frequencies, and these benefit also from reducing the size of passive components, of transformers, chokes, and whatever you have there. So these are benefiting from the switching frequencies that you apply. The traction inverter is not using a high switching frequency due to the E-motor that is driven by the traction inverter that cannot withstand those high frequencies like several hundreds of kilohertz in the onboard chargers and DC-DC. So, but they benefit from the power density that you can apply. You can use much smaller silicon carbide chips compared to an IGBT based on silicon, because the power density is so much higher. We have a factor of 10 higher electrical breakdown strengths on the silicon carbide compared to silicon.
Wow,
and
10 times.
And you have a factor of 3 of better thermal capabilities, because if you have if you're switching the same amount of power on a smaller area, you need to spread out the heat fast. And there the material properties pay in as well, with this factor 3 of better thermal capabilities.
And of course, with smaller devices, I'm guessing that also means that you can make the silicon carbide devices themselves physically smaller on a wafer, so you can get more devices out per wafer, so you can make them even more cost effective compared to a typical device who's taking 3 times to 10 times the amount of silicon surface area.
Yeah, right. And with every generation of silicon carbide chip technology that we are bringing out to the market, we will increase this performance by 20-25%. And this means that, as a rule of thumb, the chip area is reduced by half of that. So 20% performance increase in on resistance is paying into 10% as chip area. And this saves a lot of money.
And then on top of that, like you say, with the heat dissipation, you can use smaller heat sinks, or you need to dump less heat, which in turn means, easier thermal management and cooling. So then things can get physically smaller. And it honestly sort of makes a lot of sense, because I do feel like that sometimes engineers tend to look at the price of a part a bit too much. So they say like, oh, silicon carbide device, let's say it was, go back a few years ago where it was a bit more expensive than an IGBT. Someone goes, oh, why would I use that? It's too expensive. But what you don't realize is that you're actually saving money on the heat sink, the energy you're saving, the PCB space has gone down, you can have a smaller device, less weight, less magnetics. So it saves costs in other areas as well. And I'm guessing that is still the case. So to me, I get the impression that if you are going to build a high power system today, a silicon carbide device is kind of really the only option. But am I right?
So for the traction inverter, driving a car with an 800 volt battery technology, it is already today clear that a silicon carbide based inverter is costing less than an IGBT one. On the 400 volt battery, it is not that clear yet, but with every generation moving forward, the silicon carbide will gain more and more of the market there as well.
The gap is just getting bigger between the two, yeah. And as you see, the silicon carbide is just becoming better and better. And we're not even, I don't know if this is going to be possible, but imagine if we get to 300 millimeter wafers. Suddenly then, if you can make such large wafers, and suddenly you're talking about an even bigger surface area, more yields, better device count and quality control. And this kind of sort of leads me to think about how you guys, Bosch, as a business, are trying to lead this market. And that kind of leads me to the next question, which is that with silicon carbide technologies becoming more and more important, how is Bosch trying to position itself as a leader in this industry?
Well, we definitely want to have a position within the top 5 of silicon carbide suppliers in the market, with a main focus on the e-mobility, so the automotive market. But we also will tackle other markets beyond that, industrial applications, railway, for instance. We also want to tackle and look into market like data centers, solid state transformers, and what else is to come. Within the automotive, we benefit from the fact that despite the semiconductor division that we have for a very long time, we're doing since 60 years, 6 decades, semiconductors in Bosch as an IDM player. Many people do not know that. Everybody knows the tier 1 business in automotive that we have. And because of
sorry. Can I just quickly ask, IDM, could you explain to me what that is, IDM?
Is an integrated device manufacturer. This means we have everything from designing the chip to manufacturing the chip, selling the chip. So it's all in-house. So we have all the services here. We do our own power modules. We do them in-house. It does not mean that we do everything in-house. If we package a discrete chip, we also use OSAT partners, as all others are doing. But there is one thing that is very special in Bosch. we have the tier one business in-house, meaning an e-axle driving a car, the inverter built into the e-axle, the onboard chargers, the DC-DC. And we have the knowledge from there what kind of semiconductor components fit best to these applications. And with this knowledge, we can build better semiconductor components. So we tweak our silicon carbide chip to fit these applications best, and we get the feedback from our in-house customer that is using this kind of chips and power modules. Beyond that,
and that's interesting, because when you talk about building a family of devices, you're involved with every step of the power handling. So everything from power coming out of the battery being charged and being drawn off, all the way to when it gets finally into the motor, the Bosch family line is there. And as a result, you can best match your parts with each other, so they always make sure that they're working at the best efficiencies.
Right, and we also know that they are performant enough, they are robust enough. We get any kind of special application cases, short circuit cases, for instance. So we know very well where's the edge towards we need to design the semiconductor components, and this gives us the benefit that on the one side we do not need to over-design, over-engineer the devices, and on the other side it gives us also feedback that our parts will survive the use cases in the applications they need to be used in. That is very interesting. But we are not only selling to in-house customers, we are also selling our devices in competition to the in-house tier business to outside customers. And in silicon carbide, there is a speciality, because we even started to sell products to outside customers earlier than we used the products for internal.
And it's interesting when you mention my device families, and I say this because I personally have I sort of have a very nice opinion of Bosch, because I use a lot of Bosch sensors, because I've designed sort of circuits like environmental sensors, temperature, all that kind of thing. And of course, if someone says to me, what are you going to use? BME 280 or something like that, it's like the first thing that pops to my mind. But it kind of makes me wonder whether companies like Bosch should actually when you go look for a part, you could be like asked, what are you designing? And you tell them what they're designing, and it gives you the whole family chain of all the devices that could work together in that. So like, for example, your power module, your battery charger, all this kind of stuff, and you sort of see the whole thing working together, which is very, very cool. And with that said, I'm kind of curious as to what it is that how have your customers reacted to your SiC technologies, and what would you say has been their biggest challenge when integrating SiC into their applications?
So first of all, the customers trust the Bosch brand. This is where it all starts with. So they know
I trust the Bosch brand, and I'll say that right now, because they're very good sensors. But carry on.
Thank you for that. So they know when they talk to Bosch, we have an engineering mindset, we have an innovation mindset, but we also have a quality mindset, and they know if they buy a part from Bosch, they can trust that the parts will work in the application. They also acknowledge that as we have this tier one business in-house, and as we also do using parts for in-house, that they will get parts that suit the applications best. This is also where they put trust in. And to be honest, with many of the customers that we have globally, we have a lot of semiconductor business from other areas, like ASIC business, integrated circuits, like MEMS-based sensor business. So they know us for a longer while. So they know that they can work with us, and they trust us that in the silicon carbide space, it will be pretty much the same way of working than they know from the other areas.
And but when it comes to challenges, because one big challenge that I know that that sort of silicon carbide faces is the fact that you can't drive it like a typical transistor. You can't just put your typical BJT, MOSFET drivers onto these things. You have to have a specific type of circuit. And is that a solution that Bosch provides to match with their own silicon carbide technologies?
So what we offer to the market is a gate driver, a very sophisticated gate driver that can drive the silicon carbide chips. This is maybe in the world the highest end device you can think of in terms of parameters that you can tune in the control of the silicon carbide chips. And this is a first device that we sell to the market now. We have a generation to come that is also tackling the less high-end segment, I would say, so the more mainstream ones. But we know also from this tier one down to semiconductor play very well how to control the devices, how to use them best, how to use them in a way that they are very performant in terms also of WLTP performance, for instance.
And that's been a challenge which I've seen with other providers in the past. When silicon carbide first came out, people had to design their own gate drivers, and it kind of meant that engineers were a bit sort of hesitant to sort of try the technology. But in your case, what you're saying, Bosch has gone, not only are we providing these high power silicon carbide devices, we have the gate drivers too, which then match and pair together, and you don't have to worry about the implementation as much as maybe you would if you had to design it from scratch.
Right. Yeah.
Now, one thing I want to quickly ask you about silicon carbide, because everybody's making silicon carbide devices, is what would you say differentiates your technology from others? Because, as I said, everyone's making it these days, but something has to be different. So what is it that makes a Bosch silicon carbide device different?
So we want to be an innovation leader. We want to stay in the very top of the innovation leaders in the silicon carbide. And it all starts with the basic architecture of the chip. There is a planar device and there's a trench device. Yeah. We started directly with trench devices. And there are not many trench players out, very, very few, that manage to get the trench transistor to the robustness level the applications need. We managed to do so. We have
just very quick. Sorry, trench. When you say trench, we're talking about the very deep sort of wells that you put into the planar part of the device.
Mm-hmm. Right.
Yeah.
So this is the benefit of the trench devices. As you're using this third dimension, going into the device by etching in this trench, you have a much smaller pitch of your devices. So you have smaller devices that can switch the same amount of power. They are more performant. And this becomes more and more important because the planar devices at a certain point in time will face an end of the roadmap issue because they cannot shrink further down. And then everybody needs to switch to trench. We are already ahead because we have trenches in the market since 5 years and we know that they work well and our customers are happy with them.
Oh, sorry, that's interesting. So you're saying that when you've got the trench, you're making use of the sort of the vertical space as opposed to the horizontal space. So if you've got a planar transistor, you have to sort of spread it out on this sort of plane to try and create the channels to work. But if you go down, effectively, is it like your gate is not here? Is it sort of like going into the trench itself when you've got the two channels, the sides of the channel sort of going down like that? Right.
And let me explain why we choose to go to trench directly. We have a long experience in trench etching from silicon, especially from our MEMS sensors, where about 30 years ago, Bosch introduced the so-called deep reactive ion etching technology that made it possible to create these kind of trenches with very steep walls, with a high aspect ratio. And we moved this process from silicon to silicon carbide longer time ago already and learned how to make a perfect trench etched into this new material.
And then as a result, with your new devices, or should I say, as you make adjustments and advances in your devices, since you're already using trench, in theory, you can effectively just increase the height of your wafer, the thickness of it, and you'll get effectively more space for the trench. Which means you can create even higher energy density devices compared to trying to reduce sort of the planar size.
Yeah. So the whole game of this, the silicon carbide chip, the MOSFETs, are always a vertical device. So the current flows through the wafer and ends up at the backside of the wafer. So the MOSFET has mainly 4 core elements that pay into this on-state resistance. This is the channel region, and that's where the trench device comes in, because the channel is then formed to the vertical and is not consuming so much lateral space. Then we have the JFET region below, where you can really tweak the transistor in terms of performance versus robustness. Then you have the drift region that is blocking the voltage you have. So in a 1200 volt MOSFET, you have a higher, lower doped, thicker, lower doped drift region than in a 750 volt device. And then you have the basic substrate which gives you another term of iron resistant, depending on how thick that is, how thick the final device is. And in the channel region, especially, this trench part pays in.
Fantastic. And when it comes to sort of like the future of Bosch and silicon carbide, what would you say is your roadmap, your intentions, what you guys would like to achieve, without giving away too much details?
So we have a roadmap for 1200 and 750 volt devices, and we will continue those from today's generation 2 to generation 5. We have a clear plan. Every 2 to 2.5 years, we will shoot out a new generation very fast, even faster than some of the competitors. And the generation sequence is built on each other. So with every generation, we are introducing a so-called design element, a new thing, in all of these 4 different layers I explained earlier, and they will build on each other. So meaning what I'm bringing in generation 3 is a design element I build on again in generation 4, and then I need it again in generation 5. So it's a step-by-step, well-thought-through roadmap that is built on each other to stay at the forefront of the innovation leaders.
And very, very quickly, are you guys going to be at Embedded World this year, 2026, March?
We are there, but we are not displaying the silicon carbide. So
that's a shame.
we are at many conferences. I will be in Tokyo at the Automotive World next week, also giving a speech on our products there. We will be at PCIM.
PCIM. That's the one I should have asked about, because that's the power IC one. We'll be there too as well, I believe.
Yeah,
so,
sure.
And hopefully you guys will have your silicon carbide devices there.
Yeah, sure. We will definitely show them there.
Absolutely fantastic. Now, just before we wrap up this podcast, I've got just one more question for you. For the audience who are watching this video and want to know more about Bosch solutions, what would you recommend that they do?
So first of all, it's absolutely instrumental for us that everybody knows that Bosch is also doing semiconductors and that we have silicon carbide. And then I would recommend them to familiarize with e-mobility, with driving and using and trying out an electric-driven car. Because what is currently a headache for all of us playing in the silicon carbide market is the delay in e-mobility penetration, especially in Europe. And this has to do with certain anxieties of the customers, the end customers, in types of how far can I go with a car, how can I charge, do I have enough infrastructure? Familiarize with yourself and gain real life experience. Once you have gained that, I'm 100% sure you will drive an electric driven car. Once you have had one, you will never switch back to the combustion engine driven car. So gain real life experience. This is my recommendation.
Fantastic. Thank you ever so much for being here today. It's been an absolute pleasure.
Thank you, also from my side.